talk series in digital humanities, hosted by the Research Institute for the Humanities at the Chinese University of Hong Kong. I'm Professor McManus, and today it's my delight and pleasure to introduce Professor Daniele Macuglia, who's an assistant professor at Peking University, Beida, where he works within the Academy for Advanced Interdisciplinary Studies, the Department of the History of Science, Technology, and Medicine. He has a really very fascinating and unusual background. He was a student of physics at the University of Pavia before embarking on his PhD in the history and philosophy of science at the great University of Chicago. He has published widely on the history of science and technology from the early modern period, so from Galileo and Newton to the present. He, however, will be talking to us today on the very interesting topic of visual mindscapes in computer simulations, from Canaletto's perspective to molecular movies. So without further ado, I'll pass the virtual microphone over to our speaker, Professor Macuglia. Daniele, the floor is yours.
Thank you very much. Thank you very much for this kind invitation. It is a real pleasure for me to join you virtually from Beijing. I hope one day I can come to visit. Well, let me say to the audience that I first met Professor McManus thanks to the introduction, an introduction by Ada Palmer when he was a postdoctoral fellow at the University of Chicago's Institute on the Formation of Knowledge. And I think you were the first postdoctoral fellow at that institute. And our first meeting was over a very nice lunch in a small restaurant in Hyde Park. And I was immediately struck by Professor McManus' personality. And I was very happy to see the development of his academic journey, which recently earned him the Dan Davis Prize, which is remarkable, as the first scholar from an Asian university to receive the honor. And I have to say that Professor McManus is exceptionally humble and a thoughtful person, and these are qualities that distinguish him, and it is not so simple to find this in many situations. And so a few months ago, he extended an invitation to give a lecture in this series, and I'm very grateful for. And I would like to extend my thanks to everyone who made this event possible, particularly Bashma Locke from the Research Institute for the Humanities, and Kitty Sue, the Digital Scholarship Librarian at the CUHK Library. Okay, so let's see if I can share my screen, if everything works. Okay, yes. So basically, I will be talking about something which I started to delve on a few months ago, and I had the opportunity to be in a conversation with Martin Karplus, who is a Nobel Prize winning theoretical chemist, known for his work on the development of molecular dynamic simulations. And his research focused on understanding the movements of molecules, particularly proteins, using computers, using computational methods. Essentially, when we talk about molecular simulations, we are talking about computational techniques that are used to model the behavior of atoms and molecules and to predict their temporal evolution based on the fundamental laws of physics. And there are, as you can see in this slide, two different major types of molecular simulations: molecular dynamics and Monte Carlo simulations. Molecular dynamics basically is a kind of simulation that solves Newton's equation of motion to generate time-dependent trajectories and allow researchers to follow the precise interactions and the atomic movements in real time. In contrast, Monte Carlo simulations rely on statistical sampling algorithms to explore the thermodynamic properties and the equilibrium states of a molecular system by generating random configurations and assessing their probabilities based on the system's energy landscape. But this is just a very quick introduction. I don't want to talk about this during this lecture. What I want to say is that visualization techniques are extremely important in both molecular dynamics and Monte Carlo simulations, and they are used to interpret the complex data that these methods generate. So, for example, in MD, molecular dynamic simulations, visualizations display time-dependent trajectories of molecules and offer a way to observe how atomic positions and conformations of a particular molecular system evolve over time. And this is something that allows scientists to identify key structural changes, interactions, and reaction pathways that would be difficult to capture from numerical data alone. In contrast, in the case of molecular Monte Carlo simulations, which are used primarily to study equilibrium properties and explore the energy landscape of molecular systems, they rely on visual representations such as probability distributions, energy contour maps, and configuration spaces. And these tools basically help researchers interpret the statistical distribution of possible molecular states and, identify the most stable and energetically favorable conformations. So in the early 1970s, actually all through the 1970s, biological sciences and molecular dynamic simulations in biological sciences were limited by static visual representations that could only capture molecular structure at discrete points in time, making it difficult to understand dynamic processes such as chemical reaction and molecular rearrangements. Here you can see an example. We will talk about this visualization in a few seconds. So the problem was that we had only two fixed endpoints before and after the simulation, and it was basically impossible to get all the nuances that you can get by including a dynamic component in it. So to overcome these limitations, as I will explain in a second, Martin Karplus and his team at Harvard University introduced molecular animations, which basically transformed static images into dynamic visual sequences. And this innovation fundamentally changed the way molecular interactions are visualized and the way in which they were communicated, and enabled scientists to analyze continuous motions and conformational changes over time. Interestingly, Karplus drew inspiration from the art of Canaletto to improve the perception of depth and motion. As you might know, Canaletto was an 18th century Venetian painter famous for his precise and detailed landscape paintings, particularly of Venice, but not only Venice, also we have wonderful landscapes depicting English landscapes. So his mastery of perspective and also the use of optical devices, such as the camera obscura, basically allowed him to create highly accurate and immersive depictions of architectural spaces. And Karplus said, from analyzing Canaletto's painting, I concluded that perspective could best be shown by expressing the desired depth in and out the plane as an exponential function. And this shift basically translated depth into a mathematical model that amplified the perception of depth and made nearby objects appear closer and distant objects recede more dramatically, so as to say. The influence of Canaletto's art is actually evident in the first animated sequences or molecular movies that Karplus and his group were able to make, which laid the groundwork for the more sophisticated films that followed. As far as the current scholarship in art history indicates, Canaletto did not employ exponential functions in his artwork. Nevertheless, his technique basically inspired Karplus to explore mathematical models that could achieve similar visual effects in molecular dynamic simulations. And exponential functions proved particularly effective in these visualizations due to their ability to mimic the way human vision perceives depth, whereby spatial cues are enhanced for a more intuitive and immersive experience. So throughout Karplus' research, there was actually a mixed approach that characterized his work. While static images were frequently used in publication to show before and after states of molecular processes, which are the left and the right parts of this figure, Karplus also introduced dynamic visualizations in his presentations, which provided a more intuitive, more complete representation of molecular interactions over time. Here you can see a very early example dating back to the late 1970s. These animations actually were primarily used in oral presentations to specialized audiences, where they could convey the dynamic aspects of molecular interactions that static images could not fully capture. And as new visualization tools became available, especially with the technological developments of the mid-1990s, he and his group progressively refined representations of complex chemical and biological phenomena, and they incorporated more sophisticated techniques to enhance both the accuracy and the depth of these visualizations. So while Canaletto likely, as far as we know, used a camera obscura to create detailed cityscapes, his artistic skills actually went beyond mechanical reproduction and they help to create an idealized scene that could provide a more immersive experience. In fact, vedutisti or view painters would use the camera obscura to achieve verisimilitude in a painting while enlarging known monuments so as to activate the sense of memory of the viewer. And in my opinion, this aligns with both the truth to nature and mechanical objectivity discussed by Lorraine Daston and Peter Gallison in their famous book, Objectivity. In this book, Daston and Gallison focus on epistemic virtues and these virtues, if you have had a chance to read the book, are rooted in the scientific practices of their time, and they provide essential guidelines for ensuring objectivity, accuracy, and reliability in the representation and interpretation of natural phenomena. When I said truth to nature, this is a term that emphasizes the selective enhancement of images to depict an idealized, universal essence of a certain phenomenon by relying on mechanical processes and instruments to produce unbiased, standardized representations. In Canaletto's Vedute, actually, we see both approaches. Truth to nature, let me be clearer here, emphasizes the selective enhancement of images to depict an idealized universal essence of a phenomenon. And mechanical objectivity, which I mentioned before, seeks to minimize human intervention and by making use of instruments and mechanical processes to produce this unbiased, standardized representation. So in Canaletto's Vedute, I think we can see both approaches in action. The camera oscura aligns with the mechanical objectivity by accurately capturing Venice's landscape, cityscape, while his artistic enhancement reflect truth to nature, correcting distortions and emphasizing key elements to present an idealized version of the reality that is depicted. So I think that Canaletto is interesting because we can see both these two epistemic virtues, truth to nature and mechanical objectivity. And in this image that you can see here, the Gran Canal with Santa Maria della Salute, Canaletto used the camera oscura for a detailed wide-angle view of Venice, but his artistic intervention, such as correcting distortion and emphasizing key features, added depth and made the scene more dynamic. So similarly, early molecular visualization relied on before and after images, which, like the camera oscura outputs, provided accurate snapshots but failed to capture the dynamic nature of molecular processes. These static snapshots, much like the initial outputs of the camera obscura, provided accurate depictions, but as I said, were insufficient for conveying the continuous dynamic nature of molecular processes. And so, recognizing this limitation, scientists developed techniques that allowed for multiple frames and eventually animated sequences. And this shift from static images to more dynamic visualizations in molecular films basically reflects a shared challenge in both art and science, the need to move beyond static representation to more fully capture and communicate complex changing realities. So as I said, Karplus' work in the late 1970s introduced molecular films, which are animated sequences generated from MD simulations that captured the dynamic interactions of molecular systems. Sequentially linking static images, scientists could create a dynamic visualization of atomic interactions. And one of the earliest and most influential examples is this film created in 1977, which depicts the H plus H2 exchange reaction. As Karplus noted, soon after the calculations were done, Lee Pedersen and Keiji Morokuma, postdoctoral fellows in my group, discovered that there was a graphics laboratory at Harvard and obtained permission to make a film, which shows a series of reactive and non-reactive collisions. So with the assistance of Ivan Sauterland, who was a pioneer in computer graphics technology at Harvard, these films were produced using cutting-edge techniques of the time. So the two panels here present distinct scenarios of the H plus H2 interactions as captured in the early molecular dynamics simulations by Karplus and his team. The left panel illustrates reactive collisions where a hydrogen atom approaches the diatomic molecule and leads to chemical reactions. And the right panel, in contrast, shows non-reactive collisions. Importantly, these films employed a sophisticated approach to depicting depth and perspective. As Karplus explained, in making the film, a question arose as to how to represent the perspective. If the radius of the atomic circles was varied linearly with a distance in or in front or in back, the perspective was difficult to achieve. So we had to find a better way of showing the perspective. Drawing inspiration from the Venetian painter Canaletto, Karplus applied an exponential function to represent depth, where objects nearer to the viewer appeared larger, and this was something that enhanced the three-dimensional effect on a two-dimensional screen. What I did, Karplus recalls, was to look at the paintings of Canaletto in Visit to Venice and compare the actual distances with how he presented them in his paintings. I found that he seemed to use an approximate exponential law, e to the a times r, where r is the distance out of the plane and a is a coefficient whose value I don't remember. If I had published the result, there were many things that I did which were not published, he said. Perhaps there would be a Karplus law in art theory, as well as the Karplus equation in nuclear magnetic resonance. So this culminated in what he insightfully suggested could be considered to be the second Karplus equation. And this conceptual approach, although not formally published, stemmed from Karplus' empirical fitting of an exponential function to model perspective in molecular visualizations and provided a bridge between abstract mathematical formulations and their visual representations. I remember, he said, I remember joking when I described this in a lecture that should be known as the second Karplus equation. And here he was referring to the to his Eugene Wigner Distinguished Lecture on November 7, 2017 at Oak Ridge National Laboratory. And he also said, I tried various functional forms to fit what I was using to show perspective and found that the exponential function gave the best fit. Okay, now I will tell you something a bit more technical, just for 1 minute, and then I will delve into some epistemological considerations. So in 1995, there was the release of VMD, Visual Molecular Dynamics, that was really a significant step forward in molecular visualization tools. It was developed at the University of Illinois, Urbana-Champaign, by Klaus Schulten and his group. And this was a software that permitted researchers to visualize, animate, and analyze large biomolecular systems and offered a detailed view of molecular dynamic simulations. So basically, Schulten's goal was to create a virtual environment where researchers could interact with molecular structures in a more intuitive and immersive way, like being inside the molecular world. So this tool went beyond simply watching molecules move. Researchers could manipulate structures in real time. They could, for example, rotate them, zooming in on specific atomic interactions, or they could alter bond angles to observe how these changes affected the molecule's shape or its behavior. And this ability to dynamically engage with molecular data, I argue, represented a big philosophical shift. So visualization wasn't just a way to represent reality anymore. Rather, it became an integral part of how scientific knowledge was created. Let me speed up a bit. So now I enter into the core of what I want to say. The idea is that traditionally, scholarly discussion in the history and philosophy of science have focused on static images as fundamental tools for visualizing phenomena. However, as I noted earlier, scientific visualization has undergone a major transformation in recent years. And there was a remarkable epistemological shift that demands expanding existing theoretical frameworks. So in this context, I want to discuss the concept of visual mindscapes as an epistemological tool to describe how dynamic and interactive visualizations in contemporary molecular simulations and other scientific fields integrate with cognitive processes. Visual mindscapes differ from static images in that they are not passive snapshots, but they are active, evolving visual environments that allow scientists to manipulate variables, to explore hypotheses, and refine models in real time. So while traditional images, of course, remain important, visual mindscapes provide an immersive, manipulable space that mirrors, that mirrors, no. Sorry about that. I lost my track now. So I was saying that traditional images, of course, remain important. visual mindscapes provide an immersive environment that mirrors the fluid and complex nature of phenomena like protein folding, but also in other fields such as gravitational wave patterns or even climate change projections over decades. And this dynamic engagement with visual data basically extends the capacity of scientific representation beyond static depictions. And this is something that I argue necessitates new theoretical frameworks to account for how these visual tools co-construct knowledge through interactive engagement. So the shift towards dynamic visualizations builds directly on, as you can see in this slide, on Ian Hacking's concept of representing and intervening, which argues that scientific representations are not passive depictions of reality, but actively shape how scientists engage with and understand phenomena. So in molecular simulations, Hacking's principles take on a new dimension. While Hacking's framework sees scientific representations as tools that enable scientists to intervene in physical experiments, molecular simulation extends this idea by making the representation itself a virtual experimental space. Dynamic visualizations, such as those produced by VMD, basically enable scientists to manipulate molecular configurations or energy states within the visual model itself and observe their immediate impact on the system. And this is something that goes beyond Hacking's concept, where intervention typically occurs through experimental manipulations or external setups, such as adjusting magnetic fields in a cloud chamber to observe particle trajectories, or through the interpretative engagement with static representations, such as analyzing electron microscope images to identify, I don't know, cell structures, or studying crystallographic diffraction patterns to deduce certain atomic arrangements. So the real-time feedback in molecular simulations transforms the representations into an interactive space for virtual experimentations, where hypotheses can be tested and refined dynamically within the visualized environment. So molecular simulations do not simply facilitate interventions, they make the representation itself a continuous interactive inquiry, which fundamentally alters the relationship between representation and scientific experimentation. And this shift in visualizing aligns with Gallison's concept of trading zones, where disciplines converge, exchanging methodologies and creating shared epistemic framework. As you might know, in trading zones, share tools such as standardized techniques, but also computational models and visualizations serve as a sort of a lingua franca that enhances communication between disciplines. And these shared resources facilitate the integration of diverse disciplinary approaches and foster collaboration and innovation. However, visual mindscape go beyond traditional trading zones and boundary objects. In fact, boundary objects such as species list in ecology, blueprints in engineering, or maybe maps in geology, are essentially adaptable tools that enable different communities to work together by interpreting these objects in context-specific ways. Although they allow for flexible interpretation and cross-disciplinary exchange, boundary objects do not actively produce new knowledge. In contrast, visual mindscape in dynamic molecular simulation transform the process of scientific inquiry itself. Through the real-time engagement and the interactive feedback loops that they entail, dynamic visualizations transcend the role of boundary object, and instead of, merely translating knowledge between different fields, they become generative spaces that co-construct new knowledge by enabling scientists to conduct virtual experiment within the visualized environment. And this real-time interactivity allows researchers to directly, as I said, test hypotheses, explore emergent patterns, and refine models as the system evolves. So visual mindscapes do not just serve as a lingua franca, they create entirely new epistemic spaces that reshape how disciplines engage with one another and how they study complex phenomena. So you can see in this slide there is also a book, a famous book by Latour, and Latour's analysis of visual inscriptions demonstrates that static visualizations tools such as graphs or tables basically do more than represent data. They actively shape the construction, the stabilization, and the dissemination of scientific knowledge. In his view, visual inscriptions are not passive records. They are entities that transform transient observations into stable, transportable entities that can be circulated, scrutinized, and built upon within and across research networks. For example, a graph that captures the correlation between temperature and pressure in an experiment does not simply reflect data. It becomes a reference point that scientists across different institutions can share, discuss, and refine as they construct new hypotheses or design related experiments. However, visual mindscapes in molecular simulation go beyond this notion of static inscriptions, because these are dynamic visualizations that are not fixed, are not transportable in the same way. They are interactive. They are real-time tools that allow scientists to manipulate and refine models as they run, which effectively creates an environment of virtual experimentation, as I said. So while Latour's inscription stabilizes knowledge by making it transportable and interpretable, visual mindscape function as epistemic engines that produce new knowledge. They basically enable scientists to engage directly with complex phenomena, testing hypotheses, exploring unexpected behavior, and updating models based on real-time feedback. So rather than simply stabilizing interpretations, visual mindscape co-construct scientific understanding through a continuous process of feedback, interpretation, and adjustment. And this shift means that scientists are not just passively interpreting stabilized data, rather, they actively participate in the ongoing evolution of models and theories, and this is a level of engagement that static inscription alone cannot achieve. So, from the perspective of visual mindscape, objectivity is not a static endpoint, but a dynamic, emergent property shaped by continuous interactions between visualization tools, cognitive processes, and the phenomena under study. So, in traditional frameworks, objectivity was defined by the removal of human influence, striving for neutral, bias-free representation through standardized procedures. In contrast, visual mindscapes position objectivity as something that is, as I said, co-constructed through active engagement with interactive, manipulable visualizations. And here, achieving objectivity involves not passively recording data, but iteratively refining models based on real-time adjustments and ongoing feedback, which is something that makes it sensitive to context and sensitive to the evolving understanding of the system. So one of the key epistemic virtues, which I would describe to define dynamic visualizations, is iterative accuracy. I think this is an epistemic virtue that can provide a good initial label for characterizing these molecular mindscapes. And in this case, this virtue basically emphasizes the ongoing refinement of scientific understanding through active engagement with evolving data. So this virtue highlights the importance of repeated cycles of visualizations, experimentation, and interpretation, where each iteration leads to a more sophisticated and accurate understanding of the system being studied. So in contrast to traditional notions of precision, which is often tied to capturing a single definitive snapshot, iterative accuracy applies to dynamic systems where the complexity of phenomena requires constant revision and improvement. Another key epistemic value is interactive engagement, which draws from the traditional virtue of trained judgment. And this emphasizes the scientist's role in manipulating and interpreting visual data. In fact, traditional approaches to objectivity often emphasize minimizing the observer's influence to ensure consistent and standardized representation of phenomena, prioritizing a form of a detachment to eliminate, as I said before, personal biases and maintain data integrity. However, interactive engagement suggests that objectivity can also emerge from the scientist's continuous interaction with the dynamic system. And in this view, the scientist does not simply observe, but actively participates in the modeling process, refining and adjusting simulations in response to new data and insights. Contextual adaptability refers to the ability to adjust visualization tools and methods to the unique requirements of the phenomena being studied. This virtue acknowledges that different scientific challenges, such as, I don't know, tracking fast molecular changes or capturing rare transitions, require tailored visualization techniques. For example, while some phenomena might be effectively captured through static images, others, especially those involving rapid dynamic processes, demand real-time dynamic visualizations to accurately represent the evolving system. Emergent objectivity is an epistemic virtue that suggests that objectivity arises from the dynamic interaction between the scientist, visualization tools, and the phenomena under study, rather than from passive observation. So, drawing from Latour's actor network theory, this concept suggests that scientific knowledge is co-constructed through the continuous interaction of scientists, tools, and phenomena. So Latour emphasizes that the stabilization of facts and the closure of black boxes are the result of complex negotiations between actors, including scientists, instruments, and the very phenomena being studied. As he highlights, to picture the task of someone who wishes to establish a fact, you have to imagine a chain of thousands of people necessary to turn the first statement into a black box, and where each of them may or may not unpredictably transmit the statement, modify it, alter it, or turn into an artifact. How is it possible to master the future fate of the statement, of a statement that is the outcome of the behavior of all those faithless allies? The question is all the more difficult since the actors are doing something to the black box. Even in the best of cases, they do not simply transmit it, but add elements to their own by modifying the argument, strengthening it, and incorporating it into new context. So if we go back to the previous slide, consequently, emergent objectivity, I would say, reflect a process whereby scientific knowledge and the interpretation of phenomena are constantly negotiated and refined through ongoing interactions with visualization tools and other actors in the scientific network. In molecular simulation, objectivity is not a fixed endpoint, but I argue is something that emerges as scientists engage with visualizations while they adjust parameters and iteratively refine their models based on observations. So in classical experimental science, objectivity was often idealized as something that could be reached through standardized methods, rigorous measurement, and the elimination of subjectivity. And the goal was to produce unbiased, repeatable observations or results, often seen as a final or stable representation of reality. While in practice, scientists would revisit and refine this result, the conceptual idea of objectivity was static. An example of this classical view of objectivity can be found in early microscopy, particularly in the 19th century, when scientists sought to create standardized images of biological specimens. One well-known case involves the creation of botanical atlases by scientists such as Wilhelm Hofmeister. And these atlases were meant to provide definitive, objective representation of plants, emphasizing the truth to nature I mentioned before by capturing the most typical or ideal forms of a species. And a more contemporary example of this classical view of objectivity can be seen in X-ray crystallography during the 20th century, particularly in the work on DNA's structure by Rosalind Franklin, James Watson, and Francis Crick. X-ray crystallography, which was used to create detailed images of molecular structure, sought to generate precise, standardized data that could be interpreted as an accurate, objective representation of molecular reality. So now, in molecular simulation, this interactive and evolving process is not simply a practical necessity, but is a defining feature of the methodology. Because molecular systems are inherently complex, dynamic, and sensitive to various parameters such as temperature, pressure, molecular configuration. Reaching objective understanding is not a matter of achieving a single fixed depiction. Instead, objectivity here involves continuously refining the model to capture the full complexity of the phenomena under study. And this means that unlike traditional scientific practices where objectivity is framed as a stable or final representation, objectivity in molecular simulation is a moving target, constantly shifting as scientists update their models in response to real-time feedback and new insights. Thus, objectivity is not absent, but it is reconceptualized as a state of dynamic alignment between the evolving model and the complex realities that the model aims to depict. So this reconceptualization of objectivity as a dynamic alignment means that objectivity is not absent, of course. It is redefined. And with this, I mean that in traditional frameworks, objectivity was about achieving a final, unbiased depiction by removing human influence. But in molecular simulations, objectivity is a property of the interactive process itself. It emerges when the visualization tool, the researcher, and the system being studied reach a state of coherence. For example, during a protein folding simulation, objectivity is realized when real-time adjustment to force fields or solvent parameters lead to a model that accurately captures both known folding pathways and unexpected intermediate states. And here, objectivity is not a static endpoint, but a state of model system alignment that is constantly evolving. So objectivity in this context means achieving a sort of a dynamic equilibrium between what is represented in the model and what is observed experimentally, which is something that allows the visualization to serve as a reliable guide for prediction. So it involves continually refining the model to ensure it reflects the complex reality of the phenomenon being studied, making objectivity, as I said, a moving target and it in an iterative balance that is achieved through constant feedback and adjustment. And this dynamic form of objectivity, while provisional, is no less rigorous. It provides a robust framework for understanding and predicting behaviors that static models would fail to capture. So I have 6 more minutes. So in their work, Duston and Gallison trace the historical evolution of objectivity across a broad range of scientific enterprises, from natural history and taxonomy to physics and medical imaging, where the goal was to create a standardized representation that minimize subjective interference. And this model has been highly effective in producing reliable, reproducible scientific knowledge for centuries and serving as a foundational practice for a variety of fields, such as in anatomical illustration, crystallography, and observational astronomy. Within these domains, objectivity is framed as a stable, static endpoint, an image or result that is free from distortion introduced by human interpretation, which is achieved by adhering strictly to mechanical or methodological processes. However, the concept of objectivity in molecular simulations introduces a new dimension to this framework, one that complements Duston and Gallison's model. Instead of aiming for a single bias-free representation, this version of objectivity is based on dynamic engagement, achieved through iterative refinement and continuous realignment between the model and the phenomena being studied. Such a model is particularly relevant for scientific domains where the systems are inherently complex, adaptive, and non-linear, including climate modeling, ecological simulations, computational neurosciences, not just molecular simulations. So in these fields, objectivity emerges as a state of equilibrium between theory and visualization, evolving as new variables are introduced and the model's predictions are continuously tested and adjusted. So this interplay between scientists' interpretative actions and the evolving data leads to a form of objectivity that is fluid, responsive, and continually shaped by the tools and methods employed in the investigation. So let's go back to the previous slide. I just say that the final epistemic virtue I'm currently working on is epistemic fluidity, which reflects the adaptive and evolving nature of scientific knowledge, especially in dynamic systems where complex phenomena require continuous refinement of models and methodologies. So epistemic fluidity involves the ability to seamlessly transition between different theoretical frameworks, scales of analysis, or research strategies as new data and insights emerge, maintaining the relevance and the accuracy of scientific models over time. How? So the emergence of molecular films in the late 1960s, informed by Canaletto's perspectival style and exemplified by Karplus's conceptual second equation, marked an epistemological shift from static representation to dynamic and eventually interactive visualizations. In fact, tools like VMD have redefined how scientists engage with molecular phenomena and enables real-time explorations and manipulation of complex systems. And this innovation goes beyond traditional virtues like mechanical objectivity, exemplified by the self-disciplined observer who strives to eliminate personal bias, or trained judgment, which is associated with the expert practitioner who discerns patterns through experience. Instead, the dynamic visualization require a new kind of scientific persona, what we might call the epistemic navigator. The epistemic navigator thrives in environments of complexity and uncertainty where objectivity is achieved through continuous interaction, continuous hypothesis testing, and model refinement. So this persona embraces active engagement with the visual model using real-time manipulation to probe multiple possibilities and reveal hidden patterns. And I have actually a variety of historical examples to share to prove this part. So just as the rise of mechanical objectivity shaped by a scientist focused on precision and restraint, the epistemic navigator embodies a mindset of adaptive exploration and also creative experimentation, which blurs the line between theory and observation. So from Canaletto's Venice to Karplus molecular films, and now also to cutting-edge advances in machine learning, the pursuit of enhancing our cognitive and perceptual capabilities through visualizations has constantly pushed the boundaries of what can be known. And with each technological advance, new dimensions of complexity emerge, which alters the landscape of scientific inquiry and transform the very nature of objectivity itself. So I think it is exactly 1 hour, and I could stop here.
Thank you, Daniele, for that tremendously interesting and wide-ranging presentation. I learned a lot, and I was also reminded of some interesting things that I used to know about the history of science. So it's great. So we we now have about half an hour for sort of questions and discussion. I'll let you sort of rest for a moment. But what we normally do is we ask for participants to type their questions in the chat, and then I will relay these questions to you, and we can have a sort of a discussion. And then we tend to finish with 2 standard questions as well.
Okay.
So that's
Well,
our
let me
that's
say
our
that
plan. Yeah.
this is something that is still ongoing,
Mm,
but I wanted to present it anyway. I have been working with Martin Karplus for a few years now,
mm,
and he came out one day with this idea of exploring a bit more the epistemological framework of visualizations, dynamic visualizations. And
mm,
so I started working on this research topic in August, and I'm
mm,
still refining it. So it is far from being completely, I would say, clear, and also completely exhaustive.
mm,
But what I've been doing so far was to relate this idea of dynamic visualizations with what has been done already in fields such as STS and the philosophy of science,
mm,
particularly through the work of Jan Hacking, as I said, Peter Gallison, Lorraine Daston.
mm,
And what I found out is that essentially with molecular simulations, and by extension, a huge variety of nonlinear and highly complex phenomena, we are dealing with a different kind of visualization, which the traditional framework uh, adopted by philosophers and STS scholars to describe the role of visualizations in science must be updated. In fact, historians and philosophers of science working on molecular simulations are extremely rare. Basically, I'm
mm,
one of the few doing this. And so it has not been a topic that has been widely studied. But so I realized that what Daston and Gallison wrote, for example, which is absolutely extremely important and still valid,
mm,
can be uh, adapted to
mm,
this very peculiar role of visualizations in molecular simulations. And this
mm,
doesn't mean that I don't agree with them. Actually, I think what they did is absolutely impressive and extremely useful. I just want to write a few considerations on how we could handle the problem of visualizations in molecular simulations, where there
mm,
are some differences, the differences that I highlighted in my talk.
mhm. Yes, no, that's very helpful for sort of yeah, seeing what's under the hood, as the Americans say, of this project. And I agree. Yes, I mean, Dustin Garrison, their theory sort of rings true. I mean, I would argue even for some elements of historical research as well,
Mhm.
not just I guess quote unquote science. But I'm we have a couple of questions in the chat, but I'm wondering if we could maybe go back to sort of the beginning of your presentation and the kind of the Canaletto example. And so I mean, do we have any sort of I guess sort of biographical context to this? I mean, Canaletto is obviously a very well-known painter to those of us who are interested in these things. But is there some particular painting or trip to the National Gallery or to Italy that sort of
Mhm.
sparked off this this moment that you describe? I mean, how can we sort of situate this biographically in Karplus's case?
Well, I asked him the same question basically, and he
Yeah.
told me that back in the 1960s, he went to Italy and he had this idea all of a sudden. So he saw the possibility of applying this technique to molecular visualizations. And he started to think of possible mathematical expressions, and he found out that the exponential function was actually the one that more closely could uh, imitate Canaletto. I don't know why Canaletto. I don't know why this particular situation gave him this idea. Uh, he's actually very old now, and sometimes he said he cannot remember everything very well. Uh, uh, but then it's interesting to see that he went back to Harvard and he tried out some functional forms to see whether he could use the same approach in his visualizations. Of course, as I said, Canaletto, well, we don't know for sure, but Canaletto basically, we have no evidence that he used exponential functions. In fact, he basically made use of mechanical devices such as the camera oscura, but mechanical optical devices. Uh, so this idea to bridge art and mathematics is something that developed, emerged in Karplus' mind, and he tried to apply it to what he perceived to be a limiting aspect of visualizations in molecular simulations. I don't know if I answered your question.
Yes, yes, no, I mean, you did precisely.
Okay, so we have some questions.
Yes, definitely.
Okay, let's see. In what ways do drawings derived from molecular simulation facilitate communication of scientific concepts? Well, I can tell you that as um, right now, any day, I would say, I will publish an article in a journal called Historical Studies in the Natural Sciences, in which I basically worked in collaboration with a Beijing-born emeritus professor at MIT, Sidney Ip, uh, who basically played an important role in attracting the attention of the traditional molecular simulation community, which was basically composed of people from chemical physics or condensed matter physics to material science. Sidney Ip used to be a material scientist when he was working. And he was one of the people who realized the importance of using molecular simulations in material sciences. And he was one of the leading figures that basically uh, played a role in transforming material science by introducing molecular simulations in a time during the 1970s when material sciences were basically carried out through traditional experimental and theoretical approaches. So he went to Varenna in Italy to an important summer school where he was the only material scientist, and he used drawings from molecular simulations to convince the readers, the listeners, the audience there, of the importance that applying the same techniques to material science would have led. So these boundary objects are extremely important because they can bring together the so-called different epistemic cultures, and they find a reference point according to which they can understand each other. They can, in a sense, speak the same language. So in a period when molecular simulations were developing and permeating various disciplines, being able to communicate with different epistemic cultures was very important. So visualizations played a very important role in aligning different epistemic cultures and allowing for remarkable transformations, such as in material science, with the acceptance and the adoption of molecular simulations. How can they bridge the gap between complex data and visual representation? Well, it depends on the situation. So it depends on the situation. I don't have an answer for this.
Yeah.
How can VDM, VMD apply to contemporary studies? For example, history input, some old data and new data, and what changes instantly to present objective analytics.
Yeah, we have several questions in this vein. Essentially, so we have a lot of history students here, and they're sort of interested, I guess, maybe in applying what you've talked about to their own studies. I mean,
Yeah, so
there are
let me
obviously
give an
theoretical
answer.
insights and practical insights. Yeah.
Okay, so let me give an answer, which I hope can be general enough to satisfy everyone. So I have to admit that what I'm working on right now is a bit experimental, because I am finding myself in a delicate situation where I want to acknowledge the very important contributions made by scholars such as big names such as Jan Hacking, Daston, and Gallison. And in fact, I am not in any way trying to contradict what they did. I'm just trying to extend something to take into account recent developments that are becoming particularly prominent right now. And this is something that Jan Hacking did not really focus on back in the 1980s. So, in a sense, I'm trying to like write a footnote to their work, and I'm now trying to find an appropriate balance in order not to seem that I don't consider their work important. But at the same time, I want to show that with molecular simulation, something new is happening, and we need to update some theoretical frameworks that have dominated the STS and philosophy of science community. So now, what I normally do, this is, as I said, in a sort of an experimental paper I'm writing. It will take me several more months before it will be ready. And actually, I will take a screenshot of your questions here to make sure I can get all the inputs. So what I normally do, and this is important, I think, for history students, is that in my history of science research, I carry out a lot of oral history interviews. So in my research in particular, I connect with leaders in the field of molecular simulations, people who also, as you have seen, received the Nobel Prize, and I asked them what they did. So it's very oral history based, and with uh, with a lot of patience, because these are very complex topics, I try to engage directly with them and reconstruct a bigger network, engage with other people, and I try to balance an internalistic and externalistic perspective. I'm more interested in the internalistic aspect of science. So For example, I wrote an article a couple of years ago where I developed I reconstructed the history of the first molecular dynamic simulation of a protein in 1977. And this was very internalistic because I was just looking inside the scientific community. But of course, as history students for you and also for me, we should try to find a balance and look also for the broader societal, political, uh, mm, the power relationships that can affect a certain phenomena. In my case, this is a bit more difficult because I'm talking with scientists who do not really care so much about this externalistic perspective. So this is something I have to do by myself. So this means that there is no general recipe that you can follow. It is all very context dependent. In my case, I can rely on the expert judgment of scientists with whom I talk directly. And this is very important for me because some of these topics are so complex that when these people will not be among us anymore, it will be very hard for historians to understand what was going on. And these people are pretty old, so I try to move on. And for me, having an interaction with them is very important. But all of them are quite internalistic. And as historians, we have to find a way to broaden the perspective because it is our job, right? To create a more nuanced perspective and background for the development of certain processes. And so I I I think that some of the questions you ask me here are really how to say context dependent. It depends on what you are focusing on and what kind of people you are interacting with if they're still alive. But I am more than happy to be in touch with you if you have any specific history of science related questions that you think I can help you with. I would be very happy to.
I see we have an interesting question that's just popped in the chat. Maybe relates to this question.
Confirmation bias of sort. Oh. Well, this is very interesting. Well, in terms of confirmation bias, well, it is obviously it is possible, but in molecular simulations, which are completely theoretical tools, in fact, when I said experimentation before, it was in quotation marks. So a simulation is something that starts with theory, starts with a model, mathematical model, and ends up in a model. But the final word is always experimental. So if there is no agreement with the experiments, then the simulation does not have any sense. And this final experimental word actually is a feature that guarantees that confirmation bias is not eliminated but kept to a minimum level. I need to think more about this. It's an interesting question.
And maybe while we're on this kind of externalist track, I mean, my impression is that often what seems innovative in one discipline, and you suggested this already, comes from another discipline or is part of a large series of changes that is affecting multiple disciplines at the same time. So, there's sort of various post-colonial theory effects, many disciplines in the arts and humanities, social sciences, round about the same time. I mean, how would you place this within, I guess, the context of, the history of visualization and graph theory in computer science and
Oh,
mathematics?
it's a very broad and difficult problem to deal with. This is why I only mentioned very briefly that this kind of framework can be useful for other scientific problems, such as mm, climate modeling, astrophysics, um, mm, pandemics modeling. So it is not really related to molecular simulations alone. Um, However, I think it is already very difficult to it is difficult to exactly develop some framework to handle these visualizations within molecular simulations. And even by talking with other experts, philosophers, and the scientists themselves, sometimes we don't reach an agreement. So I guess that if I enlarge my scope right now, I might get lost.
Of
So,
course.
so for me now, I will well, I will have to keep working on this paper. I'm just giving it. I gave another talk. I will give another talk on this, and so I try to get inputs to improve it. But I would not feel confident now to make generalizations that can be very dangerous. So I keep focusing only on molecular simulations, and I highlighted that there are possibilities for applications also in other nonlinear, highly complex phenomena where visualizations play an important role, but I'm not really familiar with those fields, so I avoid.
Yeah. Yeah, that's fair. That's fair. So we have a couple of other questions, I think, before we move on to the onto our final section. Um, I mean, one of the things, and I think this kind of draws a couple of different questions, is I mean, so students here are not that familiar with the history of science. I think we don't have a department. Certainly in our history department, we don't have any specialists in the history of science. It's often described as a discipline at the intersection of different fields. It may not, for people in the middle, you never feel like you're between things. You always feel like you're in the middle. So maybe that is not how you actually feel. But I'm wondering if you have any sort of reflections on working on the history of science as a historian who talks to Nobel Prize winning scientists.
So it's a strange feeling because um, in a sense science is very important. It's extremely important in our society, and the figure of the historian of science is sometimes a bit not completely understood. So if you go to a history department and they see that you are a historian of science, they might say, "What?" Or so they might think you are not really a historian, you are something different. And if you talk with scientists, uh, they might think that you don't understand the science and they just say, "Why do you make me lose my time?" Some of them can actually be very impatient sometimes. Um, in my specific case, I love both science and history. And as a matter of fact, I wanted to study history for my undergraduate in Italy. And so I found a perfect discipline where I could blend these two approaches together. In fact, um, as you said, the history of science is very open to various perspectives. We My department is in the Academy for Advanced Interdisciplinary Studies, which I think is the exact location for this kind of department. Um, and so we have this flexibility to to talk to scientists and to make cross-cultural connections. But this is actually something that happens in history too. So historians can focus on economic history, political history. So it's the same thing, I think. But the history of science is something that developed in a sort of a weird way, probably, because we don't have a department of the history of economics or a department of the history of politics. Okay, so it's interesting. I would say it is still, there should be no difference in a sense. And sometimes I feel a bit strange because you don't exactly know where you fit. I mean, I know where I am, but there might be some confusion with the people you talk to. So
and yes, and identity is partly constructed by your interaction with others. So
yeah,
that's it's always the problem. Oh yeah, very interesting. And I suppose yes, you've mentioned that there are maybe coming from a place like Chicago and from an interdisciplinary program at Chicago, that was really the best place to be. And there are
for
perhaps a
me,
few for a few other places in the world where that's possible, but in
for me it was very good, and we had a very strong training in historical methods. So the social sciences at Chicago are very good, and so I was very lucky.
Yeah. Good. So we're now into our last couple of minutes. So I'll move on to our sort of final traditional questions. So the first question, and I'll just say both. The first question is, if students are interested in this topic, broadly speaking, what's the one book or article you would suggest they read? And two, what are you reading right now?
Interesting questions. So regarding the first question, I should say that there are very, very few books on the history of molecular simulations. One of them is called Computer Meets Theoretical Physics, authored by Giovanni Battimelli, Giovanni Ciccotti, and Pietro Greco, published with Springer in 2020. Battimelli is a historian of science, and it is a pretty accessible historiographical overview of molecular simulations over the second half of the 20th century. So I would recommend it. As for me, what I'm reading now, I'm reading scientific articles. So, as I said, the scholarship in the history of molecular simulation is not really existent. I can say that. So, but this is incredible because molecular simulations are extremely important in our society from a technological, medical, pharmaceutical perspective. And we have many of these pioneers still alive. As I said, they are old, so there is a lot of work to do, but probably because the subject matter is a bit complex and it needs a background in physics, not everyone is convinced to do that. Okay, so the historiography in the history of molecular simulation is non-existent. So as for me right now, in addition to other books I'm reading, for example, this one, it's wonderful. I read a lot in general. It's not an academic book. It's a novel by a fantastic American writer. Well, I'm reading it in Italian. David Foster Wallace. So high quality literature and scientific articles. And when I am when I think I am confident enough to have grasped the essential features of a scientific article, then I reach out to the author and I try to have a Zoom call with him or her to discuss further. And so, yeah, so I even answered by telling you what I'm exactly reading right now.
Yes, that's wonderful. That's wonderful. Great. Well, yeah, that's a very it's a very interesting field and a very interesting process that you're engaged in, which is perfect for our very interdisciplinary seminar here in digital
Yeah.
humanities.
You are doing a wonderful job. I should have probably presented something more, how to say, consolidated, but I wanted to how to say, to experiment this. It is still not ready. But I think it's interesting. So
Yeah, work in progress is gladly received. Anyway, we should probably sign off and let our participants go for their dinners here
yes,
here in Hong Kong.
and I want to thank everyone for this opportunity, and for all of your students, if they want to contact me, please encourage them to do so.
Absolutely. I'll just sign off by reminding everyone who's still on the call that we have another talk on October 28th. Lorella Viola, Conceptual Changes in Vaccine Discourse, a social media graph-based analysis of the HPV vaccine, again in Italy. So we have a bit of an Italian theme this term, which is great. Anyway, all that remains for me to do is to thank our speaker and to thank everyone else for coming. So
congratulations to you, and thank you all of you for this opportunity.
Thank you so
Thank
much,
you.
Daniele.
Good night.
Right.
Thank you.
Good night, everyone.
Bye-bye.
Bye.